welcome back to another full week of school. If you've been following along with that suggested pacing guide that I gave you, today should be August 31st, Monday. We're starting 1.5, which is probability basics. I'm giving you guys 2 days to do this lesson before we move on to 1.6. So this first one is a bit in depth, sometimes hard to understand, but I think a good problem nonetheless. So much media attention had been focused on the use of mammography for detecting breast cancer. The following table shows for 10,000 women in their 40s the number of women with positive versus negative mammograms and the number who were diagnosed with cancer versus those who were not diagnosed for 10 years. So, how accurate are mammograms at detecting cancer? So, we have the first question. What percent of 10,000 women had a positive mammogram? So, percent, remember, is part over whole. So part would be the number of women with a positive mammogram. Out of the total women, which is this 10,000, because they said 10,000. Okay, so number of women with a positive mammogram. So positive mammogram and total right here, 6,432. So 6,432 divided by 10,000 women. So these 10,000 women, over 6,000 had a positive mammogram. So what percent is that? So if you type that into your calculator, you get your decimal, turn it into a percent. We have 64% of all women have a positive, which seems like pretty terrible odds. Like you're more than halfway likely to have a positive mammogram. Like that's pretty terrifying. Part B, what percent of the 10,000 women had a cancer diagnosis? So again, and I'm sure it's getting annoying, part over a whole, but I think it's really helpful. So we're looking for the number of cancer diagnosis out of the total women, which again is at 10,000. So let's go back to our graph. Positive cancer diagnosis is 378. So we had to follow that horizontally. Cancer, 378. 378 divided by 10,000. We type that into our calculator, turn that decimal into a percent, and it's 3.8% of all women are diagnosed with cancer. All right. Part C, what percent of the women who had cancer had a positive mammogram? Okay, so I think this one, C and D, are probably our hardest questions. How do we set up our fraction? Okay, so remember, it's getting annoying, I know. Part over a whole. Okay, women who had cancer had a positive mammogram. So our total is women who had cancer. Just like I highlighted the 10,000, that was our whole. So this is our whole. And then our part is that cancer with a positive mammogram. So number of women with cancer and a positive mammogram. All right, I know that one was a little bit tricky, but just go slow. We've got this. All right, so number of women with cancer who had a positive mammogram. So that would be this number right here. Positive mammogram and the cancer diagnosis. So that is 302 divided by women with cancer, which we said already was that, which was at 378. All right, so we divide those, gives us a decimal, turn it into a percent, and we're going to round our percent. It's going to be 80% of, and this is why it's so important to label our units, because what does this 80% represent? This 80% represents the number of, or the percent of women who were diagnosed and had a positive mammogram. All right. Part D is equally as tricky as Part C, but hopefully a little bit easier since we already walked through a difficult one. What percent of the women who had a positive mammogram then had cancer? Okay, so you got that positive mammogram. So that's 63% of women who had a positive mammogram. What percent of them then went on to, in fact, have cancer? Okay, so change colors here. So we've got part over a whole. We have, just like I highlighted before, percent of women who had a positive mammogram. That's our total. Okay. Women with positive mammogram, and I'm abbreviating. And then our part is the number of women with cancer and a positive mammogram. Okay, so number of women with cancer and a positive mammogram, we've already found that number in the last problem, and that was 302 women. And our denominator is the one that's going to change. The number of women who had a positive mammogram. So positive mammogram is 6,432. So 6,432, calculator, decimal, turn it into a percent. 4.7% of women with a positive mammogram, I think I spelled that wrong. Yeah, one more M, that's okay, had cancer. All right, so notice our numbers are totally different. We had 80% in Part C and only 4.7% in Part D. Why is Part C so different from Part D? They're not the same. What do these 2% actually say about mammograms? And I get that this is definitely confusing. It took me a long time of sitting here processing what those 2% mean. I mean, if it's hard for me, I know it's gotta be confusing for most of you. So I wrote down a lot here. I kept it here from the answer key just because I didn't want to have to rewrite it, but I will explain through it. So both questions are looking at the number of women who are diagnosed with cancer and had a positive mammogram. Because that was our denominator, or that was our numerator, for both of them. That was at 302 women. Part C is looking just at the number of women who have a cancer diagnosis. Okay? So, cancer diagnosis, and then well, did you have a positive mammogram? Okay. And we're saying, well, yes, 80% of women who were diagnosed with cancer look back, oh, yeah, you had a positive mammogram. That's where that 80% is coming from. Part D is looking at the number of women who received a positive mammogram. So that positive mammogram maybe came first. So we're looking at part A. 64% of all women have a positive mammogram. And then from there, we're saying that only 4.7% of those women with a positive mammogram then go on to get diagnosed with cancer. Okay? Why are these percents so different? What does that mean? Mammograms have a very high rate of detecting cancer when it's there, 80%. However, only 5% of those positive mammograms are actually cancer. 95% of the time, it's not cancer, it's a false positive. Okay, so mammograms, I mean, I know that's really far into your future. Probably none of us are thinking about it. I know I'm not even thinking about it yet. But really high false positive rates. Okay, hopefully we were able to get through that problem. It was a really good in-depth thinking question. Thanks for hanging in with me there. I know that you're probably like scratching your brains like, oh my gosh, what did we just do? Like, this was terrible. Yes, totally, 100%. I am with you on that, but it's really important for us to try to reach a little bit further outside of our comfort zone. So if you need to take a break, go ahead, pause my video, stretch your legs. Thanks for coming back. Welcome. Unpause your video. Good job. Good set of notes right here. We're working with relative frequency. Frequency is the number of time an event occurs. So relative frequency is the ratio formed when frequency is divided by the total number. Okay, so frequency divided by whole. So kind of part over whole, like I've been saying this whole time. So if you want to read through that example there, try to make sense of it. I know it's a lot of numbers, but we got this. Question number 2, a national survey asked how many people were living in the respondent's household. So this is like our census, which I know probably none of you are old enough to fill out your census, but being 2020 and the census happens every 10 years, this was the year for the census. So if you maybe watched your parents do the census, I don't know if you did, it took literally 5 minutes. One of the questions was, how many people live in your household? So that's kind of what this information is about. So the following table shows those results. Find the relative frequency of a household with more than 8 people and interpret it. Okay, so we want to find relative frequency, household, that's not a highlighter, household with more than 8 people and interpret it. Now, the hardest part probably of this question, are we including the family with 8 people in their household? Okay. No, we're not. We're asking more than 8. More than 8. So we are looking at 9, 10, and 11 people. And apparently nobody said that they had 12 people living with them. 11 was the max. So if we looked at this data, if you want to take a step further into the data and look at it, a singular bachelor living on his own by himself, that was 695 individuals, man or women. I just don't know what the women version of a bachelorette pad, but that sounds kind of weird. Okay, so you're living by yourself, basically. 2 people, whether it's single mom, kid, single dad, kid, or a couple, what have you, 2 people. That's the most. 997 people. It was just 2 people living in the house. 3, 4, and notice that it's going down as the number increases. And then we get to 8, 9, 10, 11 people in a household, whether it's parents, two parents with a lot of kids, one parent, a lot of kids, or maybe you're living with relatives. So grandma and grandpa are living with you, or an aunt and uncle are living with you. It's just number of people in your household, not including your pets. Okay, so we want to know the relative frequency out of everybody. What percent of people have more than 8 people in their household? Okay, that was a lot. I'm sorry for talking so much. Okay, so number of households, and I sound like a computer, with more than 8 people. Good job, Sanchez bot. Okay, out of total households. All right, what was it? Well, number of households with more than 8 people, we can do that. 3 plus 1 plus 1 is 5. Excellent work, class. You are all so smart. And then out of everybody that replied, and since I'm such a genius, I'm able to just add all this up into my head. That's 2,538 individuals. I'm just kidding. I used my calculator and looked at the answer key from my computer. Okay, divide that. We get a decimal. It is 0.00197. And that is, turn it into a percent, 0.2%. 0.2%. That's not even a whole percent of households have more than 8 people. And you're like, wow, Miss Sanchez, you've got some real chicken scratch for your handwriting. I know, I'm just trying to go fast. Sorry. Okay. Other ways to interpret this, we could say 2 out of every 1,000 households have more than 8 individuals living there, or 1 out of 500 households. So I just turned this into a fraction. 0.2% is 1 out of 1,000. And then I reduced it to 1 over 500. So kind of uncommon to have a large household. It is much more common to have a smaller households, less people living with you. Yeah, okay, you can keep reading if you want to. A recent poll was conducted to try to understand consumer coffee habits. Oh, geez. Okay, complete the following table and then do the problems that follow it. So, age 18 to 44, drinking at least 1 cup per day. 357 people drink at least 1 cup of coffee a day. All right, cool. 45 to 64, pretty much the same number. 65 and older, only 197. So I guess as you get older, drink less coffee maybe. Okay, so we're going to add those up. Drinking at least 1 cup of coffee per day, regardless of your age, that is 895 individuals. And then we have those that do not drink at least 1 cup a day. So maybe they just drink the one, or no, actually they don't drink any coffee. Or maybe they drink tea. Okay, so we're going to subtract the total minus this, and we get 387. We get 177. We get 70. We get 634. Brilliant. Okay. Find the experimental probability that someone in each age group drinks at least 1 cup of coffee per day. Which age group has the highest probability? Okay, notice that the totals are different. Over here, totals are different, even though these numbers are kind of close together. A lot closer together than the totals. So we need to find the percent for each age range. So we've got 18 to 44. We have 357 individuals drinking at least 1 cup per day out of the total for 744. And that gives us 48%. So 48% of that age range drinking at least 1 cup. Then 45 to 64, we have 342 drinking at least 1 cup out of the total surveyed, which is 66%. All right, winners so far. Let's see about our 65 and older category. I said that not a lot were drinking coffee. So I said, looks like not a lot are drinking. Maybe you drink less coffee as you get older. Okay, let's see if that's true. 196 divided by 266 that were asked, and that is 74%. So my initial assumption about this data was that 65 and older doesn't drink a lot of coffee, but in fact, our grandparents are drinking a ton of coffee. The reason why that number was so low is because not a lot of 65 and older individuals were surveyed, only 200 and some versus the 700 18 to 44-year-olds. Okay. Find the experimental probability that someone over the age of 65 does not drink at least 1 cup of coffee per day. What's the fastest way to find that? Okay, so the real technical mathy way, if you didn't do part A, was to take the number that did not, which was 70, divided by the total that you surveyed. You'd type that into your calculator and you'd get 26%. Now, the faster way to find it, because you already found the percent that does not drink at least you found the percent that does drink at least 1 cup, which was 74%. You could just subtract it from 100 to find those that do not. That would be the faster way. Either way is fine with me, though. Part C, find the overall probability that someone 18 years old or older drinks at least 1 cup of coffee per day. So now we're looking at out of everybody that was surveyed, which I didn't write the answer. This was 1,529 individuals were surveyed. What was the chance that someone 18 years older? Okay, so we have 895 divided by the total, which is 58% of people of all ages drink at least 1 cup a day. So that was this total number of people that drink at least 1 cup divided by the total number of those surveyed. I kind of skipped a step there. I'm sorry. Problem number 4, we're going to skip. Yay, thanks, Miss Sanchez. Oh, you're welcome, guys. No problem. Anytime. All right. Last one. The following table shows a person's probability of experiencing certain events in the United States in 2014. So the information's a little bit old. So contracting Ebola in America, dying in a plane crash, dying from a lightning strike, dying from a bee sting, killed by a shark, or killed in a car accident. Determine approximately how many people experienced each event, assuming the population of the United States at the time was approximately 320 million. All right, so we got to do a little bit of math here. Let's pull up Desmos here. Okay, so what are the chances of contracting Ebola in America? Well, that's 1 out of 13.3 million. Okay. If you wait just a second when you type it into Desmos, after waiting a second, it splits it up into sets of 3. So you can see hundreds, thousands, millions. Okay. So that's the likelihood of contracting Ebola in America. Super, super, super small decimal. Now we're going to times that by the number of people in America. I don't even know if that's not. Yeah, that's enough numbers. Okay, so 320 million. That's my number there. So it looks like the number of people that contract Ebola in America each year is 24. Yikes. Okay. Dying in a plane crash. Since I'm using just the same setup, I'm actually going to go in here, delete the numbers I don't want, and rewrite it. Okay, so it looks like 29 individuals die in a plane crash. Dying from a lightning strike is 1 in 9.6 million. So 9.6 million. That is 33 individuals. Dying from a bee sting is 5.2 million. 52. So we got 61 individuals. Or if you want to round up, I guess it's really 62 individuals. 62. Okay. Killed by a shark is 3.7, so 37. That is 86 individuals. And killed in a car accident is 1 in 9,100. So I'm going to have to delete a lot of these numbers. 910. And that is 35,164. Or you could round to 65. So what is this saying? You're most likely to die in a car accident. However, people fear some really unlikely events. People are scared of flying in a plane. Why? Because they think the plane is going to crash and they might die. Some people are afraid of lightning, being struck by lightning. People dying from bee sting. I don't really know of many people who are afraid of dying from bee stings, aside from those that are highly allergic to bee stings. People are more afraid of the pain. People are also very afraid of sharks because they're afraid that a shark is going to kill them. But not many people are scared of driving in a car, even though you are way more likely to die in a car accident than anything else. Even if you added up all of these, still not going to come even close to dying in a car accident. So just a little side rant there. How many times greater was the probability of dying from a bee sting compared to contracting Ebola? So we're looking at bee sting compared to Ebola. We can also turn that into a fraction, which is I was going to abbreviate that to BS, but I thought someone might get mad. Okay, Ebola equals 62 bee sting divided by Ebola, which is 24, and you get 6.2. I'm not actually going to write out what that means. Okay, so we get 6.2. You are 6 times more likely to die from a bee sting than contracting Ebola in the United States. And I'm not going to write that down, even though I want you to, but I'm tired of sounding like a robot. Okay, so that's all. Homework questions are assigned. That is on your own to do. If you have any questions or need me to make a video about any of the homework, which is 1 through 5, let me know and I can